The solar system is not stationary in the cosmos. It is on a continuous journey around the center of the Milky Way, our spiral galaxy. This galactic voyage is a fundamental component of celestial movement and involves complex interactions with other stars and galactic structures. The gravity generated by the mass concentrated in the galactic center, including a supermassive black hole known as Sagittarius A star, is the driving force behind this orbit. The orbital speed of the solar system is impressive, moving at approximately 828,000 kilometers per hour, or about 230 kilometers per second. This speed is necessary to balance the gravitational pull of the galactic center and prevent us from being drawn directly toward it. Completing a full orbit around the Milky Way takes between 225 to 250 million years, a period known as a galactic year. Since the formation of the solar system, it is estimated that we have completed about 20 to 25 of these orbits. The path that the solar system follows is neither a perfect circle nor a simple ellipse. Due to gravitational disturbances from other stars, spiral arms, and interstellar gas clouds, the solar system follows a wavy trajectory through the galactic plane. This movement causes it to oscillate above and below the galaxy's midplane, resulting in a complex spiral-shaped path. The solar system is located in a specific region of the Milky Way known as the Orion Arm, a smaller spiral structure situated between larger arms such as Sagittarius and Perseus. This location is quite special, as it contains stars of various ages and nebulae, offering a wealth of information about star formation processes. The distance from the solar system to the galactic center is significant, around 27,000 light-years, placing it in a relatively quiet area of the galactic disk. The solar system's movement within the Orion Arm is dynamic and involves shifts relative to stars and interstellar gas clouds. Unlike the idea of a fixed journey, this movement is characterized by small variations in speed and trajectory, shaped by gravitational interactions with nearby objects. Massive stars and star clusters can alter the solar system's course within the arm, causing it to follow winding, non-linear paths. These local interactions also have implications for the more distant environment of the solar system, such as the Oort cloud, which is susceptible to disturbances caused by nearby massive objects. Such disturbances can trigger the movement of comets toward the inner solar system, increasing the likelihood of impacts with planets. It is believed that these dynamic changes in the solar environment have contributed to significant events on Earth, such as mass extinctions and drastic climate changes. The local group of galaxies, which the Milky Way is a part of, is a relatively small cluster compared to larger galactic clusters, but it contains over 50 galaxies. This group includes galaxies like Andromeda and the Triangulum Galaxy, as well as several dwarf galaxies. Together, these galaxies are not only orbiting each other, but also moving collectively toward larger cosmic structures, such as the Virgo cluster. The local group's movement is directed toward the Great Attractor, a massive concentration of galaxies and matter, which exerts a strong gravitational pull on the group. The collective movement of the local group is influenced by various gravitational forces, including the pull from nearby galaxies like those in the Virgo cluster. While the galaxies in the local group are relatively close to each other in cosmological terms, they are also moving away from more distant structures due to the accelerated expansion of the universe. This cosmic expansion, known as Hubble's expansion, keeps the local group relatively isolated, with its galaxies gravitationally bound to each other, but moving away from galaxies outside this group. While most of the galaxies in the local group orbit the Milky Way or Andromeda stably, these two galaxies are on an inevitable collision course. This future collision between the Milky Way and Andromeda represents a significant event in the evolution of the local group, marking the merger of its two largest galaxies. The collision will not only drastically change the structure of both galaxies, but also impact the distribution of their stars, planetary systems, and even the eventual formation of new stars. Regarding the collision between the Milky Way and Andromeda, the two galaxies are approaching each other at a speed of about 110 kilometers per second, moving toward a galactic merger. It is estimated that this collision will occur in approximately 4 billion years, and when it happens, the celestial landscape will be transformed. The stars in both galaxies are unlikely to collide directly due to the vast distances between them, but intense gravitational interactions will distort their shapes and alter the orbits of many stars. This may result in stars being ejected from the galactic system or reorganized into new orbits. When the collision occurs, both the Milky Way and Andromeda will merge, forming a new giant elliptical galaxy, which astronomers call Milkomeda or Lactomeda. The merger may trigger intense star formation, as the gas and dust clouds of the two galaxies will be compressed and collapse to form new stars. This will transform the resulting galaxy into a new structure, very different from the spiral galaxies that exist today. The Earth and the solar system will likely be in a new orbit relative to the galactic center after the merger, but it is uncertain whether our system will be directly affected by the gravitational forces of the collision. In any case, the cosmic landscape will be profoundly altered. The night sky, if life still exists on Earth or elsewhere in the solar system, will be dotted with new stars and nebulae, the product of violent interactions between these two cosmic giants. The cosmic microwave background, CMB, is the residual radiation from the Big Bang that permeates the entire universe and serves as a kind of cosmic reference for measuring the movement of astronomical objects on a large scale. In relation to this radiation, the solar system moves at a speed of about 600 kilometers per second. This movement is known as peculiar motion and reflects both the velocity of the Milky Way and the local group of galaxies toward a specific region of the universe, compared to the CMB. This reference is one of the most accurate ways to measure the movement of large cosmic structures, providing a clear view of how we move relative to the fabric of space. The movement of the solar system in relation to the CMB also raises questions about the forces influencing this trajectory. Some of these forces can be attributed to massive cosmic structures, such as superclusters of galaxies, which exert enormous gravitational pull. Studies suggest that the movement of our local group may be affected by these colossal structures, including the Great Attractor and the Shapley supercluster. These dense regions of matter may be pulling our galaxy, contributing to the movement we observe in relation to the CMB. In addition to the known structures, an intriguing theory that has emerged is that of dark flow, which proposes that there is an as-yet unexplained gravitational influence coming from beyond the observable universe, pulling galaxies in a specific direction. Although still a topic of debate and study, the idea of dark flow adds a layer of mystery to our understanding of why the solar system, the Milky Way, and the local group are moving in this way, relative to the CMB. If confirmed, this theory could change our view of the composition and forces at play in the cosmos, on scales beyond what we can directly observe. While the movement in relation to the CMB is defined on a cosmic scale, there are also closer influences that affect the solar system's trajectory. The gravity of nearby stars, for example, can slightly alter the course of the solar system over its journey through the galaxy. These gravitational disturbances do not cause dramatic changes, but can nudge the solar system off course on small scales over millions of years. Occasionally, a star may pass relatively close to the solar system, such as the event predicted for the star Gliese 710 in about 1.3 million years, which could influence the Oort cloud and send comets into the inner solar system. In addition to stellar influences, the solar system also passes through different regions of the galaxy, some denser in gas and interstellar dust. These regions, known as interstellar clouds, can impact the heliosphere, the bubble of charged particles emitted by the sun that protects the solar system from external cosmic radiation. When the solar system enters denser interstellar clouds, the pressure on the heliosphere increases, which can result in greater exposure to cosmic radiation, potentially affecting space weather and even atmospheric and geological conditions on Earth. This interaction with interstellar clouds may also influence the solar system's evolution on a larger scale. If the solar system passes through a dense enough cloud, it could lead to significant compression of the heliosphere, allowing more energetic particles to enter the inner solar system. If you enjoyed this video and want to keep exploring the mysteries of the universe with me, don't forget to subscribe to the channel and hit the notification bell so you don't miss any new content about science, space, and incredible curiosities.